Okay, we have two parts of our website that are not homework assignments. You have no codes to turn in today, but we'll be playing with a race to the trillion game and the error propagation playground. So if you go to your weekly to-do list, they are here. I will open them. And I should introduce you to them. Your homework this week is just to do a few problems. We're almost done with the textbook. Start taking some practice finals as much as you can. I know Thanksgiving will get in the way. You have 10 problems to write up as always. No more 10 exercises with codes, just play with the race to trillion and error propagation. And if you want, meet me Sunday and catch up on achievements. To-do list okay? So the race to the trillion game is bigger. If you've played idle games like Cookie Clicker, they do this sort of thing. I made a spreadsheet because I'm a boring math person. And how the spreadsheet works is we're going to have 4 of you play a game trying to get as many points as you can. So if you want to play, raise your hand in Zoom or shout out or something like that, and I will put your name here. I'm actually going to make a copy. So we will have this one separate from the others. No one wants to be a brave volunteer and pick things?
I'll be happy to play.
Rick and Jackie are saying, so we could just have the 2 of them. Anyone else want to play?
I'll try it.
No, I'll get rid of player 4 for now. Okay, so on your turn, we have columns that are going to add up numbers. If you don't spend any points, that's fine. You will get either 0 or 1 point. So I'm going to say on Rick's first turn, he's spending 0. And then this randomizes and he gets 0 points. He is still at 0. Makes sense? If you want to actually pick editing on this, it should be open to you because it's in our class folder. Jackie Osol got 0, Journey Osol got, oh, she gets 1, so she is at 1 point. So on the round 2, Rick and Jackie are stuck on this. They're going to roll again. And you can actually use Control R to roll. So Rick can roll, and did it roll for him? It is going. Okay, so if I roll for Rick, he gets a point. If I roll for Jackie, did that change? I guess the 4 is to change. Okay, she gets a point. But Journey now gets to move to the second column. She can spend her point and get between 2 and 5. So she's going to come out ahead. So I'll click over here, Control R for her. She is now up to 2 points. So she spent that point and she's up to 2. See how this is building up? Okay, so Rick and Jackie, you don't really have a choice. I assume you want to spend 1 to get bigger.
Yep.
So Rick is now at 5 and Jackie is now at 5. Okay. Journey, you don't have 10 to spend. So you're going to spend 1. And you also got a 5. So you spent 1 of those, but you got 5 more. Now you're up to 6. And so on. To make things go faster, because of class time, I'm just going to give everyone 100 points. Let us skip down to this row. Now you can spend 100 of your points and you'll get between 200 and 500.
Let's do that. Yes, please.
Okay, so Rick, Control R, we're looking at that row, right? So he gets 240. Not sure why it's doing that. He spent 100, so that's gone. Jackie going to do the same. So she gets 324. That's spent. And maybe Control R is pasting. Shouldn't be. Oh well. And Journey, are you going to do the same thing? I assume so. So you got 215 and spent your 100 and so on. So we're going to build up bigger and bigger. Once you get to 1,000 points, then you would be getting 2,000 to 5,000 and so on. So you can play this game at home, especially if you have young family members that would think this is interesting to watch the numbers get big. The reason we can do this is to look at this column of scientific notation. We talked about this last week, so hopefully this is review, but 1 is 1 times 10 to the 0. Because 10 to the 0 is 1. 10 is 10 times, and 1 times 10 to the first, because 10 to the first is just 10, and 1 times 10 squared. 10 squared is 100, right? 1 times 10 cubed. So this E plus means 10 to that power. So if I wanted to make a chart about it, then we could write it as 1 times 10 to the 1, 1 times 10 squared, 1 times, whoops, nope, I did it wrong. No one is hollering out when I make a mistake. There we go, 10 to the 0 is 1. Why is 10 to the 0 1? Because of this pattern. It doesn't really mean anything to multiply 10 by itself 0 times, but to make the pattern work. And if you have a calculator, you would input this as 1, and then your EXP button, and then 0, or 1, and your EXP button, and 1, and so on down the pattern. I have now gotten better at using my Windows calculator or other calculators to show you. We'll get to some actual problems. So play with this if you want, and it will let you kind of get some sense of how much bigger a billion is than a trillion. Okay, back to here. So we've now done this one. When we're looking in the textbook about scientific notation, let me now open that up. Page 231. Then let's see what the textbook says. So it's giving you examples. Here's different numbers. We could write 4,000 as 4 times 1,000, or 4 times 10 to the third. We could write 4 thousandths as 4 times 1,000th, or 4 times 10 to the third on the denominator. And by convention, we put a negative exponent to mean we're really talking about the denominator. If you haven't seen negative exponents, don't worry. You should have seen them because you read The Angry Chemist and know that they just mean do decimal point scoots to the left instead of to the right. Squeezing this on over here. Oops. Then this 3 means 3 decimal scoots to the right, and a -3 means 3 decimal scoots to the left. And if you understand this and this, then you understand scientific notation. We're taking a big number and saying, we don't want to write it all out with all of its zeros. That's a pain in the neck. So we'll use 10 with an exponent to say how many scoots are happening. I'll go back to the book. So again, 3 means 3 scoots, -3 means 3 scoots the other direction. They talk about it nice and officially, and here they draw their picture about scoots. So you don't have to remember my picture. And that's really all there is. They do a bunch of example problems. Can you scoot the number? Can you count how many times you scoot the number to undo this? If I have a vague issue, let's see. Let's do this one. I'm not quite sure how many times to scoot without one more rule. So I said we're done, but really we're not. I could say one, 2, 3. We'll write this as 7.8 times 10 to the -3rd. I should probably put my arrow on the other side. Or I could say maybe we started here at that side. Both of these are equivalent things. Did I start here and do 3 scoots, or did I start there and do 4 scoots? So by convention, this one is what we like, and we call it scientific notation. This one is okay, it's true, but we're not going to use it. It's not what we call scientific notation. You want to scoot the decimal point enough that this is just 1 digit. To the left of the decimal point. If you keep scooting, so you have 2 digits to the left of the decimal point or more, then that's not wrong math, but that's not scientific notation. So in all the textbook example problems, they scoot until they get just past the first thing that's not a 0, and then they stop. If you had 0.0129, you're going to stop between the 1 and the 2. As soon as you scoot past the 1, you stop, and you had 2 digits, so that's what you did. Okay, and that's all this is. They do more and more of it. They want you to be able to put them in the calculator. And if you want to be lazy, then you can just use our Desmos calculator and put it in exactly as it looks. 1.5. I don't have a calculator open, do I? Times 10 to the negative 7 times 10 exponent negative 7. Let's put some parentheses around that. And then multiply that by whatever it was, 8.2 times 10 to the third. Get your answer that way. So if the weird EXP buttons on your calculator aren't making you happy, then just use the Desmos calculator and put it in exactly like how it looks. If we were meeting in person, I would love to walk around the room. You take out your own calculator and I help you with how to press the buttons, because some of them are annoying. But since I can't do that, then there we go. Okay, questions about this? Can everyone do this example either on your calculator or on Desmos if you want to?
I have a question. Are you able to just use like the button that puts like -7 in the exponent on your calculator? Like without
Probably.
having to, okay.
Let me see real quick if I can do this on the Windows one. Yes, okay, let me share screen differently. So if the Windows calculator works like most of yours, how I would enter the same problem, I would do my 1.5, I would use the scientific notation button, and I can't use minus, I have to use the plus minus button to say -7. Now I've put in 1.5 times 10 to the -7th. Then I'm going to multiply that by 8.2 exponent times 10 to the negative times 10 to the positive third, and I will get out the same thing. Okay, back to sharing the Jamboard, and I will paste that. So to write it down again, I had to do 1.5, and I did my EXP button, then I did my plus minus button, then I did 7, and then I did multiply. To 8.2. And then I did my EXP button. And then I did 3, and then I did equal. So hopefully one of these two is enough for whatever your calculator works in. Did that answer your question, Journey?
Yes, thank you.
Okay. So homework is easy. They give you a little nice summary at the end. Put that. So all you're doing is converting things back and forth, scooting the decimal, counting how many times, writing it as a power of 10, or given the power of 10, do the decimal scoot the right number of times in the proper direction. Okay, so that was scientific notation. Let's review that by looking at the Angry Chemist essay. So in the Angry Chemist essay, then we were starting by looking at decimal point scoots, reviewing what we just said. Times 10 is 1 scoot to the right, times 100 is 2 scoots to the right, times 1,000 is 3 scoots to the right. So counting how many zeros, counting how many scoots, mathematicians wanted a word for that. So the word is logarithm. Logarithm of 10 is 1 scoot. Logarithm of 100 is 2 scoots. Logarithm of 1,000 is 3 scoots, and so on. So more about there. We'll also in English use the phrase an order of magnitude. 1 order of magnitude means times 10 bigger. 2 orders of magnitude means times 10 squared, right? Times 100 bigger, and so on. If you haven't seen the Powers of 10 video, you should do that. Why do you do this? Because earthquakes work like the game. A big earthquake doesn't go from 10 to 20 to 30. Bigger earthquakes go from 10 to 100 to 1,000. They are orders of magnitude bigger than each other, not just double or triple. So if we want to measure all of the earthquakes, then we need a logarithmic scale. We need to be counting decimal point scoots, not just the numbers. Here is that chart that we put on the Jamboard earlier. If I have 10 or 100 or 1,000, I can count how many scoots. That's the exponent for the power of 10. And if I have decimals, I'm just scooting the other direction. Everyone okay so far? Since this was homework to read, I am going a little faster. Okay, then we have avocados, Avogadro's numbers, moles, and so on. Our first example of something that is just too big to think about, 6 times 10 to the 23 is the rounded version of Avogadro's number. How big is that? Well, that much sand, grains of sand, would cover the beaches of 100,000 Earths. That many kilograms or gallons of water would cover the oceans of 100 Earths. So this is a really big number. Unless you're counting atoms or electrons or something, then it is silly to use a number this big. It's more than an Earth supply of whatever you're counting. Okay, on and on and on. We talked about molarity, which is how many moles of stuff are in a liter of distilled water. The Angry Chemist doesn't mention that we always use distilled water in the lab because he didn't want to overwhelm you, but when it says water, we mean distilled water. So even though that's such a big number, if you have something like, you know, how many molecules or atoms of something, there will be moles is the right amount to count them in. And then you get this chart. If we're just counting H plus protons and ions, whatever you want to call them, cute little cat ions because you like the picture, then there's a very small number, but quite measurable in normal distilled water. That's why it has a pH of 7 and not something bigger or smaller. The H2O will have some H pluses floating about anyway. If we add some from acid, then we can change the total and we go back to our logarithm thing. We take our pattern, how many decimal scoots is that? There's a negative sign we don't want, so we just agree to get rid of it and we call that the pH. So again, I'm going fast because reading this was homework, but the idea is that your coffee that maybe you drank this morning has a pH of about 5. What does pH 5 means? It means that the molarity went up from 1 of whatever this is, let's count, 10th, 100th, 1000th, 10,000th, 100,000th, million, 10 millionth. So normal water has a molarity of 1/10 millionth, but coffee has tenth, hundredth, thousandth, 10,000th, 100,000th. So you went from 10 millionth to 100,000th, and that's why your coffee tastes acidic. So the part that should look familiar is this part, right? This looks like the stuff with significant figures we just did. So focus on like the middle of that chart. And then because maybe you're going into chemistry, we talk about how this really works with basic things as well as acidic things. Okay, somebody wanted a review of Angry Chemist. I'm not going to call you out by name while we're recording, but was this a good enough review of Angry Chemist? Moving on. Now we're going back to some things that are kind of abstract to think about. So we know how to think about really big numbers and we know how to write them. We just spent 45 minutes talking about it. So what happens if we actually use them? If we're trying to make decisions with them, we're going to have to use them, not just write them on paper. So how does that work? So if I was a millionaire, how about somebody else? Who wants to be our hypothetical millionaire today? So I'm not just saying me. This is your chance to pretend to be a millionaire. Can I pick on you, Delcy?
Yes.
Yes. Okay. So Delcy is a millionaire. She just became a millionaire yesterday. Congratulations. She finally earned up to $1 million for her net worth. And so her net worth is about $1 million. We don't know what exactly. It probably has property and things like that. That's hard to measure precisely, right? Not just a bank account. So if she gets another quarter, what is her new net worth?
Million plus 0.25.
It's about 1 million. If I add plus 0.25, that doesn't change what I started with, right? I still have about 1 million. Okay. This actually happened. Somebody gave her a quarter. She picked one up off the street while walking around. But Delcy's net worth is still about 1 million, right? We don't know any different. If she went to a gumball machine and spent a quarter, same thing. Her net worth is still about 1 million. Okay, Delcy happens to weigh, let's just imagine you weigh 130 pounds. I am totally making that up because there we go. And she notices eggnog is now for sale at Costco and drinks a quarter pound of eggnog and enjoys it very much. Same sort of thing, right? Her weight is still probably 130 pounds. When she told us her weight was 130 pounds, Delcy probably is including her clothes. And she might not have weighed herself just now. She just knows she's about 130. So the fact that we knew she just drank some eggnog doesn't actually change what we know about her. And similarly, if she goes and exercises and knows she burns enough calories to lose a quarter pound, her weight is still about 130 pounds. Little amounts just don't come into play when you're dealing with big amounts and you're adding and subtracting. Everyone okay so far? Okay, now Dilsey, our millionaire, is planning what to do when she dies because she is a responsible millionaire and her family wants her to do good estate planning. And she is going to pay 25% of her net worth as an estate tax. Suddenly, this 0.25 matters a whole lot. Her family is going to lose a quarter of this, $250,000. Or she decides that she doesn't want to die in the US. She will move to a country that has a different currency and the exchange rate is 4 whatevers to the dollar. So how much is in her bank account now? It's not about $1 million. Every dollar will become 4 of this new currency in the new country. This 0.25 really matters now, right? She has 4 million somethings in her account. So when we multiply or divide, then tiny numbers matter just as much. When we add or subtract, they don't, when we're putting them with giant things. The same with the weight. If she has a medicine that says she should take as many milligrams as her weight times 0.25, then the 0.25 matters, even though it didn't when we were just adding. Everyone okay with my overview so far? Okay, thank you, Delzy, for letting me make up things about me. So when you have a big number and a tiny number, if you're adding and subtracting, the tiny number doesn't really come into play. You're not going to change your decision because, again, we really care about math to make decisions with this. If Rick is trying to decide how big a house he can afford, picking up a quarter off the sidewalk isn't going to change his decision. But when we're multiplying and dividing, the tiny little decimal numbers can be really important. We don't ignore them when we multiply and divide the way we might when we add or subtract. So that's why John Phillips from chemistry says, don't think of significant figures as a set of rules. Instead, mentally frame this idea as a scientific communication protocol. A protocol meaning what we've all agreed to do for expressing measurements and results to show the magnitude and the uncertainty at the same time, as well as a snapshot of the device that was used to make the measurement, all in a sweet little compact package. And to help you understand what he means like that, I'm going to look at some rulers. You're probably used to a ruler like this top one that has centimeters on one side and inches on the other. But let's imagine you had only a centimeter ruler, the second one. And let's imagine that your friend, in fact, has one without the millimeters on it. So I want to measure the area of a rectangle. I'm going to use the ruler that has centimeters and millimeters, but my friend is going to only use the ruler that has centimeters. Don't ask me why. My friend is strange that way. So zooming in, it looks to me like this is maybe 14.2 centimeters along the bottom. And going down, it's 9.5-ish. It's hard to tell. There's no little millimeter marks on that one. Does my picture make sense so far? Now my friend is messing me up. I'm not quite sure how much to trust the 10th place on my friend's measurement. If I wanted to find the area, I could. Okay. Area of a rectangle is length times width. I always write script because once I wrote it without script and put this as a 1 and got the wrong answer. Don't want to do that again. So I can pick whichever of these is length or width. And what do I get for this? 14.2 times 9.5. I get about 134.9. Square centimeters. And someone asked, is that any different from 134.9 centimeters squared? No, it's just a different way of writing the units. Since I am lecturing, I will always write this way because it's a little clearer for people to follow as I am writing and you are watching. But if I was writing just answers on a page of homework, I might do this because it saves ink, right? Anyway, should I round this? My measurements were pretty much okay to the 10th of a centimeter. Mine especially, my friends not so much. What do you think?
I guess it depends on what you're trying to communicate about the level of uncertainty. It seems that the numbers we put in both are to the tenths, and so I wouldn't round it. I would leave it in the tenths unless you're trying to tell someone that you're really not very confident about the 9.5 part.
Okay, other opinions?
Yeah, I kind of agree with Rick. I was gonna say maybe you should round it because at the end we don't really know if it's 9.5 for sure. Could be 9.6 or 9.7. So maybe rounding it would show whoever is reading it that we don't really know.
How big is a 10th of a square centimeter if I was to draw one on the Jamboard?
Tiny.
It's really tiny, right? It's just one of these little millimeters as a square. I'm not even sure I can draw it well. So I don't think we know exactly whether it's 134 or 135 if we're measuring to like put stickers that size all over it, put bathroom tiles that size all over it. So I would certainly say, no, I think that we should just say 135 and not try and brag about our accuracy. If we were chemists thinking with significant figures, we could also write this as 1.35 times 10 squared square centimeters. And in this case, we might rethink things even more. By having 2 points after the decimal place, we're questioning, we're claiming that we know this, like it's really 135 of these guys and not 140 or 130. But seeing how small these little blue things are, maybe it is that. So maybe what I should actually do is that, which would be equivalent to this. So before I ask if you follow me, then this last step is actually what the scientific community has decided is their protocol. We don't get to decide what to do. The chemists have decided as a group before we joined their group. They will take the number of decimal places in the measuring device and use that, not when they write their answer in normal numbers, but when they write their number in scientific notation. So that's what John is saying here. Significant figures are our agreement that if you know things to 1 decimal place with your measurement device, you should write your answers with 1 decimal place
So what about then with the other ruler that doesn't have the decimal place?
I'm saying that even if it's not written, I can still tell that it's about 9.5. It's closer to having a decimal place than not. I'm not completely vague about if it's 9 or 10.
Okay.
So I put it in there to show you that just because our apparatus has a certain label, unless it's like a digital scale, that doesn't really mean we trust it completely. And that's one reason they round twice here. We don't say 135, we say 140. Right? Some digital scales are awesome, but there are some wonderful experiments you can read about where people took professional chefs and had them use tablespoons and measuring cups, and then did how much variation they have. If you ask a professional chef to measure a third of a cup of flour, it varies quite a lot. Right? So just because our measuring apparatus claims to have a certain amount of accuracy, that doesn't mean we actually get that much accuracy. Something I am being fuzzy about here is this number has what they call 3 significant figures. The 1, the 4, and the 0.2 are all real things that we trust. This number has about 2, right? The 9 and the 5 that we partially trust. This one has 3, not because we have better than millimeters, but just because it went past 10. We have 14 instead of 8 or 9. So that's a level of detail the textbook doesn't care about, but you might see in a chem lab someday. Okay, now back to our book. So how does the textbook explain everything I just did with John's quotation and some rectangles? The textbook says, by the way, we care about accuracy. And we care about place value. So far, so good. You've seen that a lot. And an output can't be more precise than the input. That's what we're trying to avoid. Then the textbook does this terrible thing and talks about adding and subtracting first. We're going to skip over that and come back to it. When you multiply and divide, you need to think about significant digits, what they call significant figures. And this could be vague. If you have 1,300, then is that like about 1,300, or did you really measure it and there's not 1,301 or 1,302, but there really is 1,300 exactly. So using scientific notation lets us avoid that vagueness. We can say that anything that's not a 0, we know has been measured. Zeros in the middle of a number, we know have been measured. And zeros we write on purpose after the decimal point, we know have been measured. Otherwise, we wouldn't write those. We'd just say 2.45. But zeros in front don't count as significant. That's just telling us that we're measuring in whatever this is, tenths, hundreds, thousands, 10,000. This is micrograms instead of grams or something. And zeros after a non-decimal number, we're going to assume are rounding. This is about 16,000. And then we get back to Dilsey, our millionaire who weighs 130 pounds. If you are adding, then pay attention to what's really happening in real life. Her million stays about a million, or if you've measured something vaguely, 11,000 we've only measured vaguely, then we're going to assume that we can use whatever the more precise thing is, but that might be bragging, so let's just call this 27,000. Because we don't know if this is really 11,000 or 11,500 or 11,400. We would round it up if it was 500 or something like that. So since we don't know if this 0 should really be a 4 or not, then we'll use the least precise of our two measurement things. We'll use del Z's about 1 million, not the 0.25 cents. On the other hand, when you multiply, going back to this page, then you're going to say the number of significant figures in your answer should match your measurement tools. And if one is more vague than the other, use the lower number of significant figures so you don't brag about your accuracy. So that's John's thing. You can memorize those as a set of rules. Let's actually write them as a set of rules. If you're adding or subtracting, then assume numbers like 11,000 are rounded. And it might actually be something like 11,400. So this you can trust. But this part you can't trust. And once you can't trust anything that's less than 1,000 in your answer, you can't trust anything less than 1,000 either. If you're multiplying or dividing, then you use scientific notation. And have your answer significant digits. Is the same, or if you have to pick the least of whatever your measured amount. If you had 3 significant digits in both measurements, you get 3 significant digits in your answer. Okay, formulate the rules in better English in ways that make sense to you. I'm telling you again how to read 8.2 because they do things out of order. They really should talk about significant figures and these bullet points before they talk about, let's assume that 11,000 is a funny number. That might be 11,400. Okay, other than that, you're just following the directions. The example problems are pretty clear. 60 has only 1 significant digit because the 0 at the end of a number that's not a decimal. So the answer will have 1 and so on. Your calculator does all the work. You're just trying to figure out how much to round it. And the homework shouldn't look scary either. Again, you're just doing some arithmetic. Your calculator does the work. How much should you round it? Okay, we're not quite done. We've now talked about all this stuff. A takeaway from this is that, do I get one here? No, I don't. These are measurements this is a result. We haven't measured the area. We have measured the sides and done math to find the area. So another way to paraphrase this is the result can't be more accurate than the measurements we use to get the result. And in English, we're sloppy about this. No one is going to scold you if you say, I measure the area of this shape. But just realize that sort of officially, technically, philosophically, the area isn't something we directly measured. We could put little tiles on this until we cover it and count how many. It's not like we can't measure the area, but we didn't. We chose to measure the sides instead. Okay, let's go back over his thing again. So we've agreed on what to do. We're showing the magnitude, how big something is. And we're showing the uncertainty, how many digits come after the decimal point. And that's why we have that rule that we only get one digit to the left of the decimal point, because all the others are showing us uncertainty. How carefully did we measure? And we get like a snapshot of what device we measured with. All three of those things are in this number. So that's why the science community likes this. Okay, we've talked about this. The last thing is error propagation. So we have this error propagation playground, and I will introduce this to you. You should try it sometime this next week. If you want to send me a picture of your work, you can. It might be fun to talk about. We often have numbers that are wobbly, using my words. If I'm planning a car trip, let me make this bigger, then I don't know the price of gas. It's going to change at every gas station. I know about what the price of gas is, but I'm not sure exactly. If I am planning a recipe, then I'm not going to use measuring cups exactly the same. And my friend's oven won't be exactly the same as mine when it says 350. And so on, right? We very seldom in real life actually get stable numbers that we can trust. We're trying to make important decisions like, can I afford this house? Can I buy this car? How many people should I invite to my wedding? Whatever, using data that is kind of iffy. How many of my people I invite will actually RSVP and show up? So this is like a piece of playground equipment, but instead of a swing or a slide, it is a piece of math playground equipment. How you use it is you pick two numbers and put them in the middle numbers where it says pick a number and another number. And then you make them 5% bigger and 5% smaller, 10% bigger and 10% smaller. If you read about the 1+ trick, then you will know that to do this, I go times 1.05. The 0.05 makes it 5% bigger, and the 1 keeps the original number from disappearing. And this would be times 1.1. Getting smaller, I have to subtract the 0.05 from 1. So I'm going to do times 0.95 or times 0.9. You could also do two steps, find the 5% and just add or subtract it. So once I have my numbers, let's just pick two numbers. Somebody give me two numbers and we'll really do this.
Five.
5, okay,
42.
and 42. Okay, Rick, find these 4 numbers. I'll come back to you and have you fill them in, or have me fill them. So once we've put them in, then we have in the middle operations, and on the side some equal signs. So I'm going to say, let's start. Should we add, subtract, multiply, divide? Which operation do you want? How about we multiply? So what is 5 times 42? 210. Ready when you are, Rick.
Yeah, 5 increased by 5% is 5.25.
Okay, and that means this will be 4.75.
0.75. 42 increased by 5% is 44.1. 42 decreased by 5% is 39.1.
It would be 4.2 added, right? 46.2. Am I doing my mental math wrong?
You just increased by 10%. Oh, I'm sorry, 10%. I'm sorry, I just did it wrong. Yeah, exactly. 46.2, and that would be 37.8.
Okay, so 5.25 times 46.2 gives me 242.55. And 4.75 times 37.8 gives me 179.55. So we can see either as a change or as a percent change, if you wanted to find that, how much we are off the true answer by having our numbers uncertain. Make sense so far? You could also flip things around so that the second time it gets smaller on the top and bigger on the bottom, instead of both of them having bigger on the top. So here's some examples of people playing with it. Some examples of the percent change math. So do it a few times on either the normal or flipped version and experiment and see. Does one type of arithmetic get destroyed more than another? Get different from what the answer should be. Maybe subtraction is especially fragile or something like that. See if you discover any patterns of what makes big differences or not. Doesn't matter if the 2 numbers you pick start out close together. Ours didn't, 5 and 42 weren't, but what if you picked 5 and 6? Does that help things be stable, or does that make them more unstable if one changes? So investigate things. It's a playground. There's no right answers. And then here's a cartoon from the XKCD webcomic, and you can perhaps double check some of these claims about if you have precise numbers and garbage numbers, what happens when you put them together. What assumptions is he making? For example, when XKCD is saying precise number plus garbage is garbage, if we're talking about Delcy, a million we know, she's not sure how many quarters she finds today, we can still trust she's about a millionaire. So there we go. So hopefully this isn't just a chore, but with less time than it would take to do 10 homework problems and send me a code, you can try and say, whoa, this is really a big deal going from 2 to 0.4. What happened there that made that happen? Okay, we are done. We have talked about all of our different things. You might think the purpose of a liberal arts education is to get a better job. It's actually that you can have things to talk about at family dinners and office parties and cocktail parties. You know this because if you ask 1,000 people with a college degree, did they get the job they want? A lot of them will say no, but if you ask them, do you have more to talk about at cocktail parties? They will all say yes, but when do I actually get to go to cocktail parties? So hopefully the fact that we've done kind of interesting things about not only our math skills, not only group dynamics and how to esteem, respect, and honor people, but we sort of talked today about how to be curious in a meaningful way, what types of questions to ask about situations. How reliable could our data be? What do we do when we know it's not reliable? How do results and measurements actually fit together? And then if you want, play with error propagation. And if you had a good number and a bad number, how much of a threat is the bad number to your decision? And if you are good at all that stuff, anyone would love to have you as a chemist. They can always teach you chemistry. Okay, I'm going to stop the recording, get any last comments or feedback.